very nice, and I want to do a little bit of advertising for it. Many of you know ECT Star. We also organize workshops throughout the year. It's located in a very nice town in the north of Italy. We are always looking for exciting proposals for workshops, so please consider submitting proposals. The next deadline is in September. So I'm going to talk about something that's not perhaps central to this these workshops, not so much about multi-neutron clusters, but more generally about the emergence of clustering in nuclei. So this is the outline of my talk. Bad news for Tobias. I have a Brodsky number of slides, so he should be prepared to fight with me later. I'm going to start with some general considerations and then go into the argument why I think we could understand clustering from the two-body unitarity limit. So if you, this is a plot of the ground states of nuclei in a fashion that I like quite a lot, emphasizing the low mass systems. And so this is a plot that I stole from the internet. You see the ground states here. In blue are states, the ground states that are above threshold, and the thresholds are marked. Some of the thresholds are marked with this green circles here. So if you look at this, when you might naively think that the fact that beyond the alpha particle, we are all the ground states are relatively close to thresholds, at least close with respect to the energy of the alpha particle itself, that you might expect clustering to appear. And that, of course, you know, it's indeed the case. Now, another interesting feature of this plot is that the deuteron, the simplest non-trivial nucleus, is very close to threshold. It's characterized by a binding energy per particle that's much smaller than the rest. So that gives a clue that it might be a good idea to start with what we call the two-body unitarity limit, where we treat the binding energy of the deuteron as being zero. You know, as I hope to demonstrate, that's a very useful thing to do. So that means that the deuteron is a very large object. So if it's a very large object, it's characterized by a distance, the inverse of the binding momentum, that's much larger than the range of the force. And therefore, you expect that a good starting point is to do a multiple expansion in the interactions, start with delta function interactions, and the more complicated delta functions, derivatives of delta functions, and so on. And each of these interactions is going to have a coefficient that you either derive from QCD or fit to data. Now, these interactions being delta functions, they are singular interactions, so that means that you have to do something that you do all the time when you have singular interactions, namely you have to regularize the system. So you have to make these delta functions a bit wide, smeared, for example, with a Gaussian smearing. And that means that there is at least one parameter in this smearing that with dimensions of momenta, but this is arbitrary, so what you have to do in the end is what's called renormalization, namely you have to allow the coupling constants to be functions of this cutoff parameter in such a way that observables are not. And then what you want is to order these interactions. So on the basis of a multiple expansion, you'd expect this to be leading order, this to be subleading order, and so on. And indeed, that's the case. You can formalize this in what's called short-range effective field theory that was developed a very long time ago. And then observables are going to be an expansion in powers of the small momentum times the the range of the interaction, which I'm going to call 1 over m high, high mass scale, so that this expansion parameter is small. So you can derive order by order at the two-body level what's called the effective range expansion. It has a first term that depends only on the square root of, I did not define it here, the square root of the mass times the energy, and then you have an expansion in the powers of q over m high. And what I'm going to consider here is also the possibility of expanding other terms like this one here, 1 over the relative momentum in the center of mass times the scattering length as being also a small parameter. And that's the expansion around the unitarity limit. Why is this expansion around the unitarity limit useful? The reason is that at leading order there's no scale. If you see it, if you look at the first term in this series here, this guy here has no, apart from a trivial factor of 4 pi over m that affects all observables, it has no scale. So if there is no scale, there is, that means that there is continuous scale invariance in the problem. Scale invariance is something that comes from invariance under scale transformations. Continuous scale invariance is just what you have when the little elephant becomes the big elephant. Essentially, all the dimensions are multiplied by a factor alpha that's positive. And because we are dealing with quantum systems, then that means that the momentum goes as inverse of this factor. Because it's non-relativistic, that the energy goes as inverse 2 powers of this factor. So if there is no scale, the way to satisfy this equation can be trivially satisfied if this is 0. So that means that there is no two-body bound states in the system. So the leading order then has this continuous scale invariance at the two-body level, and then corrections will account for the explicit breaking of scale invariance perturbatively. So if you apply this to more bodies, I mean, two bodies not by itself is not that interesting, then things differ whether you are talking about two-component fermions or multi-component fermions and bosons. So in this simpler case here, which for many of you is of interest in this workshop, the case of neutrons alone, what the scale, continuous scale invariance tells you is that there are no isolated finite low energy S matrix poles. By low energy, meaning within this poles that can be recovered within this expansion in terms of delta function and its derivatives. And indeed, for example, this is one calculation done by Hans Hammer and collaborators. Hans Hammer is going to be here later, if he's not here yet. And you see that increasing A2, a multi-neutron state, a finite energy multi-neutron state disappears. Another consequence is that it's very well known is that if the number of particles increases, then again by dimensional considerations, if you introduce a scale by trapping the system in a certain volume, therefore you have a certain uniform density, then the energy per particle will have to be a universal number times the free gas energy, and this universal number is the Birch parameter. So this is all very nice and of interest in many areas, but actually what I would like to discuss ground states and their proximity to thresholds is a more general case where we have bosons and multi-component fermions. And here the surprise comes. Well, it shouldn't be so much of a surprise because already in 1935 Thomas pointed out that if you now solve the leading order system with a delta function interaction for the three-body system, for the Triton, for example, the binding energy grows with the square of the cutoff, which means that you are not renormalizing the system properly. To renormalize the system properly, you need to introduce a three-body force. This is a problem that appears in the three-body system. A three-body force also made out of delta functions. So a contact three-body force, which when you spread the delta function can be written in this form as two delta functions, and a coefficient that, as always, to guarantee renormalization needs to depend on this cutoff. Now, if you adjust this coefficient, you can obtain a finite binding energy for a state like the Triton. Now, what's interesting is that three-body force is on what we call a limit cycle. It can be written in terms of one-dimension full parameter. So that means that we have anomalous breaking of scale invariance, continuous scale invariance, and it's broken to discrete scale invariance, because when you shift this cutoff by a certain power of a fixed number, then the three-body force goes back to what it was before. And here you can see in this graph that you go by a factor of this, what I call f minus 1, the three-body force repeats. So the system at leading order has discrete scale invariance. And even though it's not perhaps as powerful as continuous scale invariance, it allows the emergence of structure. So now you can do this beyond leading order and do what's called the power counting in this effect field theory. And here is a summary of the lowest orders that were done at different times. Some are known for a long time. Expansion in terms of delta functions in the two-body system, in the three-body system. And as I said, in leading order, there are only two and three-body forces, and that they have discrete scale invariance. As subleading orders, there is a lot more. At NLO, in addition to a contribution to the two-body effective range, there is a four-body force. And then if you consider nucleons, they have the isospin can be violated by the Coulomb interaction and by contact interactions. They come also at the level of subleading order. And all these interactions can be dealt with in distorted wave perturbation theory, starting from the states generated by leading order. Now, there are two major consequences of discrete scale invariance. One is very well known. You now can satisfy at the three and more body systems, you can satisfy the equation of transformation of an energy with that finite discrete scale factor if your spectrum has is geometric, it has an exponential behavior. And the factor that enters is a factor f minus 1, which gives a factor of 515 in the energies that was discovered by Efimov a long time ago in the three-body system. Hans again has shown, was the first, I believe, to show that at the four-body system there are two levels, one deep, relatively deep by a factor of 4.6 or so, and one that's right at the threshold. And the discrete scale invariance tells you that each of these, there are now two towers of states, two geometric towers. What's interesting about this state is that it's a halo state of the three-body system plus one particle. With Tobias and Renato Higa, who is not here today, we applied, and my former student Feng Wu, we applied halo EFT to that. But that's not what I'm going to talk about. It's interesting that when, in the case of bosons, people have shown that for 5 and 6 bosons, there are more towers. So the system becomes very complicated very quickly. Now, the consequence that I want to focus about is ground state correlations. The fact that there is only one parameter at leading order means that at leading order, the binding energy per particle is going to be a set of universal numbers times the binding energy per particle of the three-body system. These numbers are known up to a certain level here. If you, and I'm going to soon show results for higher bodies, That correlation was known also in nuclear physics for a long time, is a Chion line. So if you vary this binding energy, you vary that. It can be generalized for 5 and 6 bosons as well. What we can do in practice is, because it's one parameter, I can use the three-body binding energy of the ground state to determine that parameter. And once I do that, then the binding energy of the A-body system becomes a function of, a universal function of the one of the three-body system. So you can go on and calculate the binding energies of bosons. And we've done this to up to 60 bosons with Monte Carlo. And so here is the binding energy per particle normalized by the binding energy per particle of the three-body system as a function of n. And you see, you can focus on the blue results, which are the highest cutoffs. You can see that this is the behavior of the binding energy. It starts sort of linearly in the number of particles, but then can be well fitted by a liquid drop time formula, which with some numbers that are somewhat different from what you get for helium-4, but not perhaps impossible to reach them in perturbation theory. That is something else that I'm not going to talk about today. The important message is that you have the usual saturation that you see in nuclei as well. So compare this with the semi-empirical mass formula, where you expect the volume energy plus surface energy to go qualitatively in the same shape as the case for bosons. So the hope is that we can get there in the case of fermions as well on the basis of this simple theory. Now, in the nuclear case, Daniel is here and he's going to at some point give me a hard time about how we estimate uncertainties here. So I'm going to disclose that I do that in a very naive fashion. In effect field theory, you have to have at least to some extent an a priori estimate of errors. And that's what I'm going to show here. So how do I estimate the momentum, the typical momentum in the system? If it's two-body scattering, then it's given in terms of the energy of the scattering. But when I have a bound state, maybe something related to the binding energy per particle, the binding momentum, I'm going to call, of the A-body system. Because you get this formula here if you assume that every particle contributes the same thing to the binding energy. If you compare with A2, my unitarity expansion, you'll see that, of course, in the two-body system, it either doesn't converge or converges very slowly. But if I assume that, because my physics is governed by the three-body interaction, that what determines the typical momentum is really the binding momentum of the three-body system, then the expansion, the unitary expansion, is a factor of a third. But in addition, I have the more important, perhaps, the expansion powers of Q over M high. And again, in addition to the uncertainty of estimating Q, we have the uncertainty of estimating the breakdown scale of the theory. Recent work suggests that it's quite a lot larger than what we expected. So if I make the same assumptions as above, then the expansion parameter at the two-body level is a fourth, and at the three-body and higher level is a half. So that dominates the errors in this dominates the error in the two-body system, and that dominates the error in bigger systems. So let's see how these estimates compare with data later on. So this theory does a very good job describing the nuclei up to the alpha particle. These are just two results that I've been involved with, so that's why I'm showing them. Here is the binding energy of the triton. In leading order, it's fitted. At in next to leading order, we can calculate it perturbatively and focus on what I call full unitarity here, the green line, and this is experiment. So you see that at NLO, you are already pretty close to experiment. On this plot here, you see the binding energy of the alpha particle as a function of the binding energy of the triton. So you go on a line here when you vary this parameter lambda star. So this is the Thion line, and the Thion line at leading order is relatively close to experiment. And if you just include the corrections from the departure from unitarity, you already get a Thion line that's very close to data. But this is, of course, an incomplete leading order because range is not included. And in particular, a four-body force, which I would fit to this data, is not included. So it doesn't, the level of binding energy is very useful to show the full NLO. Now, what happens beyond the alpha particle? So beyond the alpha particle, unfortunately, or fortunately, depending on your perspective, you'll find out, so these are 8 nucleons, if you want, at the unitarity limit, or 8 4-component fermions at the unitarity limit. And you see what happens as a function of the cutoff, that this state, the ground state, goes, as the cutoff increases, goes towards the go beyond the threshold and becomes unstable. And that you can see in the Monte Carlo simulation, that your walkers tend to divide into 2 separate clusters. So that suggests, and it was there is further evidence from other work, that if you impose renormalization in the theory, and the fact that you are closer to body unitarity, you have a natural clustering of multi-component fermions. Now, this is only one piece of evidence, perhaps not totally convincing. I'm going to give more. But before I give more, this is the situation so far. In my expansion, I get my deuteron here with a certain large error bar here, my triton and my helium-3 that are very well described with their error bars, my helium-4 that tends to be a bit too bound, but the error bar is humongous, and then the calculation of beryllium-8, which is of course consistent with, it's here, which is of course consistent with the threshold, given that the fact that helium-4 is up there. So the point of this is to show that, well, with these large error bars, of course, we can, in principle, describe this other stuff, and to show that we are perhaps reproducing the expectation that clustering is a natural phenomenon. The problem with this, though, is that if my leading order produces states that are not stable, how am I going to do distorted wave perturbation theory for the many-body system if I don't have a bound state, if I have a state that's clusterized, that is for example, 2 free alphas instead of a nice stable beryllium-8 state? How do I do perturbation theory on that? So the rest of my talk is going to be about more recent work where we try to go around this issue with what we call improved actions. With all that confusion at the beginning, I lost complete track of time. How am I doing? 22. Oh, I have plenty of time then. Yeah. So what is the idea? So the idea is that the leading order, I can modify my leading order, not modify my leading order, I can include in my leading order solution part of the subleading interactions without any harm to the theory. In fact, you solved the very, when I said that beryllium-8 was unstable because I lost it for large lambda, nothing obliges me to take lambda to be, the cutoff to be infinite. The only thing that the cutoff needs to be is beyond the breakdown scale of the theory. Nevertheless, I would like to keep cutoff variation as a sign that my power counting is correct and as a sign that I do not have dependence on the unphysical regulator. So the idea is to add to leading order a subset of next to leading order interactions that can be corrected at higher orders in perturbation theory, so they are really not leading order interactions. They do not need to be treated non-perturbatively as leading orders, as leading order, with some parameters that are not physical and therefore that I can vary. So for example, my leading order potential is 2 and 3 body interactions, and we add a piece that I'm calling delta V here, that can itself be broken in several pieces. And the idea is that what I add here doesn't change the results more than the error that I expect of leading order. And then at subleading order, I take a piece of that potential that I added, and I include it in the NLO, and I make in perturbation theory, like I should do at NLO, and I ensure that the change satisfies the error, is within the error of the NLO. So how does that work? There are infinite number of ways of doing this. One is something people do all the time, which is the change of what are called renormalization conditions. So I chose to start from the unitarity limit, so effectively I'm fitting my two-body coupling constant to 0 binding energy of the two-body system, but I could do something different. I could fit to the actual two-body scattering length. So in that case, my potential that I'm adding is something of the same form, so delta function interactions, but with a coefficient that now account for the scattering length. So this is a way to resum infrared effects, infrared terms that go like this. So I expect my results might improve that way. An alternative is to fit to an A-body binding energy. Dan, for example, did this zillions of years ago, where he took the two-body energy to be the one of the energy to be the one of the deuteron. You can do that. You could even take the helium-4 energy if you want, the alpha particle energy if you want. And in fact, you could take a larger energy. And this is in fact the approach that has been taken in what's called the NLO set, chiral potential, by Ekstrom. I don't know if Gaut is part of that work or not. There's nothing wrong with doing that, except that it makes it difficult to check whether the theory is breaking down as the density increases with the number of particles. So I'll prefer not to do that. And a lot of people have done calculations then with improvement that are either fitting the two-body coupling constant to the deuteron binding energy or to the scattering length. The results are qualitatively the same, and what you get now is a bit of an improvement already at the field body level, and people have done many calculations with the effect field theory that go beyond that. So lithium-6 turns out to be below I lost my threshold, but to be unstable, and but what's interesting is that if you look at N-alpha scattering, there is a very sophisticated calculation by Near here in the audience. N-alpha scattering works well, but lithium-6 is unfortunately unstable, even though I improved my action with the scattering length or the two-body binding energy. Other calculations have shown that the situation does not improve when you go to larger nuclei. There are calculations up to calcium-40, and Gauta has been included in those. Again, the systems are unstable. Before I move on from this slide, I want to acknowledge that part of this work has been done with my late colleague, Bruce Barrett, who unfortunately passed away 3 months ago. So this fact that I improved the treatment of the fuel body system and I still get unstable states again suggests that clustering is a property of this whole approach based on the fact that the deuteron has little energy. Now I put the error bars that I estimated before just to give you an idea. So the fact that these things come out to be unstable does not necessarily mean that the effect field theory is not working. It only means that I have to work a bit better to calculate the NLO by improving my leading order a bit more. A second example of improvement is one in which you not only include the effects of the effector of the scattering length, but also the two-body effective range. We did this in a simple toy model to point out a few of the features of this type of improvement. We do this by introducing a dimer field. Dan has worked on this a long time ago with a particular type of improvement where they included the full effective range at leading order. The subleading interactions that account for the effective range have been included in the leading order. Here we are allowing a fraction of the effective range to be included. And we consider a toy model where the T matrix was given by the effective range expansion truncated at some point, just to have something to compare, using the parameters from the physical parameters from the 3S1 channel. And when you do this, you find, maybe I should, let me go quickly through this. What you find is that your phase shifts, you improve the phase shifts at leading order. So this is the case x equals 0. That's the standard calculation in pi unless EFT. And you can go towards x equals 1. And what you see is that, of course, the lower orders improve. But when you do what's called the Lepage plot, where you see the deviation of the phase shift compared to data, as a function of the momentum, you see that the breakdown scale doesn't change. So let me skip that. So when you include the full effective range, you have smaller, lower order errors, but the same breakdown scale. So you are varying your central value within the error of the order without changing the breakdown scale. Also, let me skip this plot here because I'm running out of time. The not surprising moral is that just what you said, you can improve in lower orders without changing the expansion of the theory. And one thing you will notice is by looking at the bound states is that there is a range of this type of improvement that works, which is between not having the range at leading order and have the full range at leading order, but you cannot push much further than that. But this type of improvement is difficult with this dimer field that creates energy dependence. It's difficult to apply to more body systems. So we came up with a different improvement, which I would say is a partial resummation not only of the effective range, but a chain of effective range parameters. And the idea is simple. Is that we add a two-body potential and possibly a three-body potential in terms of what we call fake ranges, parameters that are going to be put in by hand and that we vary later. We apply this to atomic clusters. And we consider two sorts of improvements, one in which we improve only the two-body interaction, not the three-body, and one which will include the 2 and 3 body interaction, both with the same range. Again, this is one of an infinite number of possibilities, but this is potential 1 and 2. And to see how it works, we apply to helium-4 atoms now. We fit results for particular phenomenological potential, LM2M2, which Emiko has calculated some energy, so we can compare with her results. We fit the parameters of the FT to 2 and 3 body, and 4 body at NLO, and then compare with the exact calculations. Again, maybe I should go fast through this because it doesn't have a whole lot of that much useful information, in the sense that what we find is that when we improve in either one of these two ways, the leading order results become a bit better in general than the result without improvement, which is the dotted line. This is the exact result calculated by Emiko and others. And you see that once the cutoff increases, the results converge, and the results with the improvement get, in general, a little bit better than the no-improved results. Not much to brag about these results. If I look now at NLO, I look at the restricted, amplify this region here, and I look at NLO, and NLO the same result. The results at NLO are within the band of the improved NLO results are within the error band of the unimproved NLO results, and that shows that this type of improvement can be done in a perturbative way. Here one doesn't gain anything because there are no instability to start with. One thing that we noticed that was consistent with the other improvement is that if you now look at the improvement at NLO as a function of this improvement radius, fake range, this is an infinite, the zero range limit. And as we decrease this fake parameter, we see that indeed the results are essentially independent of this fake range until it hits a wall. And this wall is the one in which the two-body interaction is giving exactly the two-body effective range. So in this region here, the improvement is under control, while in this range here is not. So there is a limit. The improvement can be done up to a certain point where after that it becomes non-perturbative and would constitute a violation or change in the power counting. So with all this long introduction, let me show the final results, the latest results, I should say. We apply this improvement now to nuclei. Here in principle, we have two-body S-wave channels, so we can have two different types of improvement. We tie them together with the same factor. Again, is one possible improvement out of an infinite number of possibilities, and same for the three-body fake range. So we have three fake ranges. We determine them through one parameter that we can vary to simplify life, and then we choose these numbers here to feed the corresponding two-body effective ranges and the best value for the alpha particle to minimize the effect of NLO interactions. And then our potential is the potential that we had before with the type of addition that I mentioned before in terms of these three effective ranges. Now, at leading order, at NLO, leading order, we are going to have the instability if we don't improve. If we improve, we have stability, but because we have these effective ranges here, the energy is going to be a constant independent of the cutoff. Cutoff dependence will only appear at NLO. We can use that cutoff dependence to estimate the error. We took results in the region where we could do calculations. It's slightly smaller than the estimate of the NLO that we would get from simply naive dimension analysis, which would be 1/4. So here then are the results for lithium-6, carbon-12, and oxygen-16. So let me guide you through the results a little bit. So first of all, experimental threshold is here. Experimental value, this one here, is there for lithium-6. Our leading order result, as I mentioned before, leads to instability quite quickly as the cutoff varies. So this is the unimproved leading order. Notice that, well, rises quite fast, but this is a 10% effect, right? Now, the improved leading order for x equals 1, to take as an example, is this, are these points here. And on the, with x equals 0.9 is here, so they don't differ significantly. And the improved, sorry, I messed up. This is the improved leading order x equals 0.9, and this is the improved leading order x equals 1. This is the improved NLO at x equals 1. So you see that this is a variation that's quite reasonable within our expansion parameter, and this is not very far from the spread here. And the result then evaluated from the last point here for lithium-6 at NLO is this one. For carbon-12, similar situation. Threshold, experimental value, unimproved leading order, improved the leading order for x equals 0.9 and for 1, and in red, the improved leading order for x equals 1. The orange bars are for x equals 0.9. So taking the red results and from the cutoff dependence, we get this result for carbon-12, and you can compare with experiment. And similar for oxygen-16. I'm not going to go through in detail through all the curves, but then we end up getting this estimate here. So you see that at NLO, we are more or less reproducing these results. These error bars for x 0.9 are a reflection of the fact that the leading order improved for x equals 0.9 is getting closer and closer to instability, and therefore the Monte Carlo has a lot more difficulty carrying out the calculation of the ground state for the heavy nucleus. And so if I plot this, this is the plot that I showed before, and this is what we get now, currently, at NLO. So you see that we are much closer to reproducing the binding energy curve. And again, the states continue to be closer to threshold, so in a way that's perturbatively close to instability. So the chances are that these are all clustered states. Now, before I conclude, because Tobias is getting impatient here, let me mention that this is similar but not the same as other work that has been done. NIR has worked on an attempt to go beyond to account for the two-body effective range corrections without running into the Wigner bound. I think what we have here is much more general. Also, we improve also the three-body level. Some people maybe in the audience, I don't have worked on pionless potentials. Oh, certainly some people in the audience on pionless potentials that do not obey the power counting of pionless EFT, so in our cutoff dependence, so they are not an EFT. And those have good phenomenological results, but here we preserve the power counting, so the number of parameters, the corrections are perturbative and so on. But there are some issues, perhaps. we could only find, only vary in the nuclear case X over a very small range. There might be other forms of improvement. One needs to check that the results are independent of the improvement. And the growth with A might be an overestimated because for oxygen 16 it was worse than for carbon 12. So let me then conclude. I'll just leave the slide over there. So
let us thank Bira. And remember that at the end of the day we are going to have a discussion session that we can squeeze our speakers, no? But at least one, 2, 3 questions. Okay, then we are over because of the time. So, Pacheco, you want? Okay, you start with Pacheco.
Okay, your lithium 6 and your oxygen 16, you have a dependency in cutoff, right? But the lithium will not have too much. You know some feeling about that?
Yeah, sorry, in lithium, you're referring to this?
Some dependency in cutoff in oxygen 16, but for lithium not have too much
Dependence on, you mean on the cutoff? Ah, yeah. Very good question. We think that it's because, well, first of all, these are results that come out of the Monte Carlo without any thinking per se, right? But certainly there is cutoff dependence in this low energy region. We think that it stabilized pretty close just because it's a relatively dilute system, so it's less sensitive to the ultraviolet corrections that are represented by the cutoffs. That's our guess. Yeah, well, okay, that's a very good point. If there is more cutoff dependence, you would expect that if you have the system is denser, right? So the more binding energy per particle. And, oops, not this one. You see here that carbon 12 and lithium 6 are pretty close, but oxygen 16 is increasing faster, right? Now you could say, of course, also the data, the binding energy of oxygen 16, the binding energy per particle increases, but it could be that if this trend continues, that we are going to overshoot by quite a lot. That would reveal the fact that we are getting too dense a system, and in that case, we would expect also larger cutoff dependence. But it's hard to speculate at this point. I want to be optimistic and think that we are going to continue in this region here, but certainly that was part of the last point in my conclusions that we need to go to heavier nuclei. But these calculations are not so easy as you can imagine, right? These are ab initio calculations with 16 bodies. Not many people can do the 4 fermions, which not many people can do those.
Bira, did you do any calculation for hypertriton and the sign of lambda? But this would be ideal.
No, hypertriton is near specialty.
But this would be ideal for you with DFT. Why
yes.
don't you do it?
Yes.
Or the 3-neutron or tetra-neutron. This would be ideal.
It is. I would say that this is, in my mind, a more important problem first to deal with first. To try to get the trend of ground states of normal nuclei. If I understand that, then I worry about hypernuclei or other systems.
So now, Imo.
Thank you for the nice talk. I have one question concerning what you discussed in the beginning, this scale symmetry. Is there any physically relevant associated conserved quantity that corresponds to this?
I'm not conserved quantity. You're talking about specifically the continuous or the discrete one?
In the continuous case, you'd expect to have some conserved quantity via the Noether theorem, right?
Yeah, well, you could say in that sense that, so okay, it's going to have to do something with the energy momentum tensor, I guess, and I don't know which new, and therefore I also don't know in the discrete case how I would, I mean, there is a charge, a conserved charge, but I don't know exactly what it does. Maybe Dan thought more about this and knows, but yeah.
There will be more time to squeeze our speakers. So for the moment, let us thank Bira.
Okay, thank you.